So we spent the last day looking at exponents that were integers. What happens when our exponent is not an integer, when it's a fractional exponent? So we have to learn what a fractional exponent is defined as. This x to a fraction, in this case a over b, is fancy for power over root. So anytime you see a fraction that is in an exponent, the numerator represents power and the denominator represents root. And we have to remember that b cannot equal 0 because then you would have a fraction that is undefined. So let's define this power over root. If I asked you to take 16 and raise it to the 1/2 power, well, remember, the numerator means power, and the 2 means root. So this is fancy for take 16 and take the square root of it, because that's what 2 stands for, and then the 16 can be raised to the first power. We could either write it this way, or we can write it that way. In other words, you can do the power first and then the root, or you can do the root first and then the power. And that's because it doesn't matter, because let's say I had 16 to the 2/3. Well, I could rewrite that as 16, 1/3 means take the cube root of it and then square your answer. And guess what? 1/3 times 2 is 2/3. Or I could take 16 and square it first and then raise it to the 1/3 power, which means take the cube root of it, see? And a power to a power, both times when I multiply here, I get 2/3. So it doesn't matter which way you do first. My advice to you is always do the root first, because by taking a root of something, you make it into a smaller number. And therefore, it's easier to then take that smaller number and raise it to a power. All right, so let's look at some examples here. So basically, I have 3 columns here, if you can't understand what I wrote here. We have this, we have this. So the first column, I just want you to solve. And remember, this is what a fractional exponent means. It's a power over a root. So remember what I told you to do. I told you to do the root first. So if I look at this problem, this is what my brain thinks. First I do the cube root of 8, which is easy, 2. Then they want me to raise that to the second power. So 8 raised to the 2/3 power is 4. Beautiful. 81 raised to the 5/4 power. Again, I'm going to take the 4th root of 81, which is 3. And then I'm going to raise 3 to the 5th power, which is, let's see, 3 to the 5th power is 243. Now here's an interesting one, 4 to the negative 5/2 power. Well, I'm going to rewrite this here just so you can see it. There are really 3 things you have to do here. You have to take 4 and raise it to a negative, which means I'm going to end up flipping something. I have it raised to the 5th power, and I have it raised to the root power of 2. So I am first going to do the root. What is the square root of 4? 2. Now I'm going to raise that to the 5th power, which gets 32. Then the negative tells me to flip that, so my final answer is 1 over 32. Now for the next column, I just want you to rewrite this as a radical. I don't want you to solve it. I just want to say, how would we take 8 to the 2/3 and rewrite it in radical form? Well, once again, I'm going to look at this, give myself some writing room over here. And I'm going to say, well, this is root. So this means I want to do the cube root of 8. And then it's a power of 2. And I like to do my powers second. Or you could have written the cube root of 8 with the power on the inside. Next one, same thing. We kind of did it over here. I'm going to take the 4th root of 81, and then I'm going to raise it to the 5th power. And this number 7, same thing. I'm going to take the square root of 4. I'm going to raise it to the -5 power. There you have it. Now here they wanted you to, whoops, I kind of messed up my numbering here, didn't I? That would be 8. That would be 9. And that would be 10. All right, moving right along. All right, any day now. There we go, Mrs. Trillin, you got it. 15 square root. By now, hopefully you know square root can be rewritten as the 1/2 power. In fact, that's how I do square root on your calculator. For me, it's too lazy. Let's clear that out. I'm going to do something obvious here. If I want to take the square root of 64, it's too lazy for me to go second function, square root, 64 equals. I just do 64 to the 0.5 power. See, if I raise anything to the 1/2 power, it's the same thing as taking the square root. All right, 3 times the 4th root of 7. Well, that means 3, then I'm going to take 7 and raise it to the 1/4 power. Notice how 7 only gets the 1/4, not the 3. And the last one, 3 over the 4th root of 81. Once again, the 3, nothing is happening to it. It's the 81 that's getting raised to the 1/4 power because I wanted to take the 4th root of 81. But since this is in the denominator, there's also a negative involved. Because remember, negative exponents tell me to put in the denominator, or if they started in the denominator, put it in the numerator. So remember, everything in Common Core, they want to represent it by a graph. So what happens if we start putting fractional exponents? What does our graph do? So right here we have, amazingly, an equation with a fractional exponent. Well, everything you've learned about graphs still holds true. Hopefully what you're seeing in the library of graphs is all that shifting and transforming about parent functions and baby functions that you learned in 8th grade are still being held steadfast and true. So for example, this one right here is something to the 1/2 power. And maybe by now you've gotten that far and you understand that the square root function looks like that. And the reason why it's only positive, it doesn't go into the negative zone, is because we are looking for the positive square roots, or the principal square roots as they're sometimes called. And if we look at this, we want to extend that knowledge that we learned in 8th grade. We still have our intercepts. So x plus 4 equals 0 tells us that our x-intercept is -4. And it's being scaled by a factor of 6. So that means we should have a stretching of 6 going on. So if we pull out this pumpkin, yeah, I know it's December. I'm sorry. When I made this slide, it was still the fall. So when I pull this graph out, we should not be surprised, oh shocking, that our graph is indeed crossing the x-axis at -4. Hey, we're smart, we figured that out. We know the basic parent shape of a square root function looks like this, and hey, that's happening here also. And the only other thing we haven't really talked about is our end behavior, which is based on the highest degree. But yeah, we did. Since our highest degree is 1/2, we know what the basic square root function, parent function, looked like. And this lovely baby that we're dealing with has the two things we need to really remember: the stretching, where it intercepts the x-axis, and actually there's a third thing right here: where does it intercept the y-axis? Well, that's the easy part. If it intercepts the y-axis, we simply put in 0 for x. So 6 times 0 plus 4 raised to the 1/2 power. 6 times 4 to the 1/2 power. We have to do our exponents first, so that's 2. So it intercepts the y-axis at 12. Because when I put 0 in for x, I got 12 out as an answer. Now, based on those two principles, the fact that we know its x-intercept is -4, we know its y-intercept is 12, since it's raised to the 1/2 power, it should look like a square root function, which slowly increases, and voila, we've got a graph.